Okay, great. Thank you for being here. We're going to go ahead and get started, and people are going to trickle in from lunch afterwards, but I want to make sure we have enough time for the great discussion at the end. So my name is Greg Wellenius, and I am at Boston University. It's my pleasure to be co-hosting this session with John Volckens from Colorado State University. And I want to thank the HEI staff, particularly Allison and Ava, for organizing this session and inviting us to co-chair it. I'm going to start by providing an introduction and an overview to set the stage, and then we'll move on to an exciting panel of speakers, and again, leave plenty of time for questions at the end. Just so you know what my external conflicts might be. So I want to start by differentiating between tailpipe emissions and non-tailpipe emissions, and I understand that there is a transatlantic divide on whether these are non-tailpipe emissions or non-exhaust emissions, so we'll use those terms interchangeably. And as we've heard, as we know, and we had a very nice introduction yesterday about regulation, tailpipe emissions in the US and in many high-income countries are tightly regulated. And the primary source, of course, is combustion. And because of the source, that gives them a particular characteristic in terms of the particle size distribution, ranging from ultrafine to fine, and particular composition focused on sulfates and organics. In many high-income countries, including in the U.S., the exposure levels or the emission levels from tailpipe, particularly for PM2.5, has decreased dramatically over the years, and I'll show you that on the next slide. And the health impacts of traffic-related pollution broadly is well documented with a substantial literature. In contrast, non-tailpipe emissions are not directly regulated in the U.S., and the source is very different. It's primarily from mechanical abrasion, heat and evaporation, primarily from mechanical wear from brake and tires, the road abrasion, and resuspension of road dust. And because of this different set of sources, the size distribution and the composition of the non-tailpipe emissions is really different than from tailpipe emissions, ranging from fine to coarse particles, so on the bigger side, and containing lots of metals, crustal minerals, and polymers, depending on what source is is undergoing the abrasion. It's so non-tailpipe PM2.5 is an increasingly important fraction of total traffic-related particles, and I'll show you that on the next slide. And there's not a ton of evidence as to the direct health impacts of the non-tailpipe emissions, but there's increasing concern and interest in this. So just to highlight the point about the importance of non-tailpipe emissions, so in 2020, HEI held a virtual workshop to convene experts on non-tailpipe emissions and catalyze the field forward. And this is a slide that was presented in that workshop and borrowed from the UK, and it shows that for PM2.5, you see that tailpipe emissions of PM2.5 have decreased dramatically since 2020, but that non-tailpipe emissions have stayed the same or increased slightly over that same time period, such that now the non-tailpipe emissions component of PM2.5 is a much larger fraction of total PM2.5 from vehicles. So as part of that workshop, one of the goals was to identify what are the key evidence gaps, and you can see the three bullets here. So the evidence gaps identified were to improve characterization of non-tailpipe emissions, to build consensus on which measures best represent non-tailpipe emissions for use in exposure studies and human health impacts or health effects studies, and to better characterize then human exposure and the actual health effects. And so in 2021, our HEI released an RFA 21-1 with goals that matched those three evidence gaps. So you can read them there, but they're validating exposure indicators to disentangle the contributions from tailpipe versus non-tailpipe emissions, to develop approaches to measure the total or model the total or process-specific, as in brake wear, tire wear, et cetera, emissions in near-road environments for use in human exposure assessment. And then finally, to characterize human exposure and health burden of these emissions. I'll get back to which studies were funded, and we'll hear a lot more about that in just a second. But in the interim, in 2022, HEI, of course, released the incredibly important systematic review of traffic-related air pollution, and you can have a QR code there if you haven't read it. This is essential reading. It doesn't focus on non-tailpipe emissions, but it does in there highlight how few studies have examined non-tailpipe emissions and the increasing importance of documenting those emissions in the changing transportation landscape. And just out very recently, earlier this month or last month, I forget, so Meredith Franklin, who is in the room, you can ask her for more details of this, but published a previously funded study, and this is HEI Report 241, looking at non-tailpipe emissions and respiratory function in the children's health study. So the agenda for this session is to hear first from those two studies that were funded under RFA 21-1. So we'll hear from Chris Griffiths and James Scales, and we'll hear then separately from Greg Evans. For those two funded studies, we'll hear some reflections from my co-chair, John Volckens, who's on the review committee. And then we'll hear from Sangju Yoon from the California Air Resources Board and a perspective from Paolo Mazzatorta from the Tire Industry Project. And then hopefully we'll leave a substantial amount of time for conversation and discussion at the end. So with that, I will pass it to Chris.
How do I get it to go forward? Oh, yeah. So thanks to the Health Effects Institute and the Review Committee for funding and guiding our work. So HEI asked for studies to better characterize exposures and health effects of non-tailpipe particulates, and these were to be in a vulnerable population. So in response, we proposed the Iona study, and our hypothesis was that non-tailpipe particulates would drive clinically significant adverse health effects in adults with asthma. So Iona is a randomized crossover design study in a real-world environment, and in this, adults with asthma are exposed in random order to three contrasting exposure environments. The first is Marylebone Road. These are in London. The first is Marylebone Road, a heavy traffic stop-go site emphasizing brake wear. The second is White City. That's a fast freeway environment emphasizing tire and road wear. And Honor Oak Park is a background site away from traffic, acting as a comparator site. So participants exercise right next to, or in one case on top of, the monitoring stations for 2.5 hours with assessments before, during, after, and the following day. And so perhaps some key features of this study design are that because the participants are exercising right next to the monitors, we have a very clear idea of the exposures that they're experiencing. Secondly, each of the participants in this design acts as their own control, so this strengthens the power of the study to detect adverse effects. And finally, we have two co-primary outcome measures, a respiratory physiological measure, FEV1, forced expiratory volume in 1 second, and an immunological measurement, IL-6 from nasal washings, and we're able to triangulate the results across these two different contrasting outcome measures. So with that, I'll hand over to James.
Right, hello. Okay, let's skip that one. So at the super sites, we have EXACT and ACSM systems, which we used to monitor the elemental composition of PM at these sites. We then used positive matrix factorization to convert those elemental fingerprints into source variables. We were able to identify a brake wear source and a tire and road wear source. We did have a look at trying to identify separate variables of tire wear and road wear, but we weren't able to. probably because in reality they are one and the same in the ambient air anyway. We were able to establish other variables such as train wear and things, which we were able to put into our health regression models later on to adjust for confounding. And I'll point out that there's a lot going on this chart, but I'll just point out in the direction that the brake wear is comprised of a lot of elements of high oxidative potential, such as barium, iron, and things like that. That's a bit of foreshadowing for some of the results I'll present later on. Once we'd source apportioned, we applied a scaling factor to give ourselves a mass estimates for these exposures. And you'll see at the top of each of these stacked bar charts is a black dot. The black dot represents the measured PM mass at each site. And then the stacked bar charts are our estimated sources at each of these 3 sites. When we take one of the variables as an example, we look at for brake wear here. We've plotted it temporally, and we can see a nice twin peak on each weekday. So what we're seeing here is the brake wear source exposures are occurring on a cycle that we'd expect to see in traffic flows in this area. So giving us a confidence in what we're seeing. We also see on these charts a nice big gradient difference between the grey lines there, the Marylebone Road site, which was our a priori hypothesized brake wear site, contrasting to the lowest scores at the White City, which was our Tyrone Roadwear site, and Honoret Park, which was our urban background. So we were able to identify identify sources from these elemental compositions, and then we were able to identify sites with good gradients. So moving to the health models, we have our primary outcomes of FEV1 and FVC, and we see significant site differences from the traffic site compared to urban control, and for both FEV1 and IL6. Again, Marylebone Road is the brake wear site. Again, and now we start adding into pollutants into the models. So along the top, you see the lung function measures, FEV1, FVC, and then the bottom rows are airway resistance measures from oscillometry. Looking at the plots, they are showing 3 measurement points changes from baseline. So you have halfway through the exposure, end of exposure, and the day following. What we see is a relatively quiet to NO2, so a proxy measure for exhaust gases, and then we see lung function reduces acutely during the exposures, and then we see airway resistance increasing following the exposure and staying elevated the day after. When we get to the exciting bits, so we include source variables into the models, we see what we think is 2 distinct signatures. We see the Tyrone Road wear producing a reduction in central airway, so the lung function measurements the day following the exposures, and then we see brake wear having an increase in airway resistance, particularly R5, R20, which is the small airways at the distal ends of the airway system. This aligns with our IL6 findings, which follow the exact same trace as the R5, R20, which if you allow us to speculate a little bit, we would say that this is because the brake wear is driven by the high oxidative potential of the metals in there. So in summary, we were able to successfully source apportion different NTE variables. We think we've seen 2 different physiological patterns off the back of this. Our next moves are to develop a large epidemiological study, talk to Chris and Greg about Nexus, and I would like to try and validate these findings in a chamber study where there's a lot less ambient confounding going on. Thank you to everyone on the study team, and that's me.
Thank you so much, and you're right on time. So next we'll hear from Greg Evans, University of Toronto.
Good afternoon, everybody, and thank you for the opportunity to present a few of the results from our HEI-funded study. Study was called IMPACT. It was actually one of the graduate students who came up with that clever acronym. So if we go to the next slide, here we go. Big green button. There we go. So the idea here was to throw every method that we had at hand to try to do field measurements to evaluate the contributions of non-exhaust emissions from brakes and tires in order to constrain it. By using many different methods, we would be able to come up with estimates from a number of different ways and come up with a better estimate of what the non-exhaust contribution is to PM 2.5 and PM 10. So we wanted to characterize the temporal patterns, the spatial patterns. We wanted to improve the methods, differentiate them, and we wanted to see if we coupled methods with data analysis methods, we could come up with further insights. So it was a lot of work. We had a fantastic team of graduate students. We had 3 campaigns, one for the fall, winter, and summer. We had 40 fixed sites across the city that we made measurements at, filter measurements that we analyzed chemically, we analyzed for oxidative potential. We had Ogawa badge for analyzing NOx. We had 2 high time resolution sites where we used some of the same instruments that James described so that we could get much richer insight into the characteristics. One was in Toronto, second was in Vancouver. We did mobile sampling where we traveled approximately 11,000 kilometers. When we say we, I mean my graduate students. And we did hotspot sampling as well. So we tried every approach that we could, or when we did sampling in subways as well, and then we tried every data analysis method that we could as well, in terms of source apportionment using positive matrix factorization that James introduced, land use regression, coupling land use regression with positive matrix factorization, using residual analysis that Mike Jarrett introduced us to, and combining it in different ways. So I'm going to highlight a few select results to answer 3 research questions that we had. The full report will be coming out in a few months where you can see a much better description of what we did. So first of all, what is the contribution of non-tailpipe emissions? So you can see in this figure here, we have 4 sites that we looked at. This was the high time resolution instruments. So we had a highway site in Toronto. We had a truck route site. We had background measurements at 2 sites. And you can see a real difference between the contributions to fine particulate matter of the road dust, the brake wear, and the exhaust emissions, which are shown in gray. Very different between when you're right beside a road and when you're right in the background, at least 300 meters away from the road. We did the same sort of analysis for coarse. This was based on filters. Once we applied the receptor modeling, which is what's being shown here, we found a sulfur-rich factor we'd never seen before. I put tire with 3 question marks on it, just to indicate that it did not correspond with sulfate in PM 2.5. This was not the usual sulfate. It seemed to be higher beside roads than away from roads, which suggests a local traffic influence. However, I really don't believe it's possible that this is all from tires, because tires does include sulfur, I should say. We believe this may be due to sulfate that is being deposited on some of the road dust particles. But this is quite speculative, so the 3 question marks. We could see how it varies over the day, so you can see the peaks at rush hour, whether it was in Toronto and Vancouver. At the bottom there, you have the tailpipe emissions, and what you'll be able to see from this, in Toronto, the tailpipe emissions shown in blue approximately matched the non-tailpipe emissions, whereas at the truck route site, which was in Vancouver, where it's the main route to the port, the exhaust emissions were higher, and that's not surprising given all the trucks that were involved. So to summarize it, here are a few percentages. I'm comparing whether we used high time resolution instruments or the 24-hour filters. We used data for filters that was collected over 6 years, so we used a lot of historic data. The high time resolution instruments were operated for a year, collecting data every 30 minutes. And exhaust contributes about 14% when you're beside a highway. Downtown, it was about 7%. And the brake wear was the main one. The main point here is that the tires were incredibly difficult to resolve. The contribution for the tires was quite small, so you see the less than signs that are there. The truck route in Vancouver had 25% from the exhaust emissions, not surprising given all the trucks on the route. But you can get an indication of the contribution to the others, the brake wear being the main one and the road dust was smaller. One of the questions we had was how can we quantify the contribution of the tires? We did this in a couple ways. We collected samples and we analyzed them by pyrolysis GC-MS for the rubber content, for the content of the additives as well. And based upon that, it was less than 5%. 3 to 4% is what we saw. So it was small and tough to resolve. We also used the receptor modeling. We used zinc as a marker, and we came up with 1 to 2%, but that is probably an overestimate as well because there are other sources of zinc as well. What we did for the rubber is we looked at synthetic rubber, natural rubber. We multiplied it by this factor of 4, which is a really rough estimate in that the rubber makes up about half the mass of tire, and then you account for how much gravel or other things are in the tires by another factor of 2. That is very, very approximate, and you get this less than 5%. It's still small. One of the things that we found is the actual concentrations of rubber seem to be similar across the city, regardless of whether we were right beside a major highway, right beside a road, or at a background site. And so that starts to imply that there are other sources of rubber, which we found quite confusing, and that we need to probe, because if there is other sources of rubber for our fine particulate, then using rubber as a marker does not work all that well. The coarse, I mentioned the sulfur-rich factor. It contributed 20 to 30%, but we don't believe that this is mostly from tires. It's from a small amount coming from the tires. It may be due, as I said, to SO2 deposited on the road dust. So here's how they vary spatially. I've just got a couple maps. This was done by land use regression with Kriegen. These first results are from the mobile sampling, where we drove the 11,000 kilometers. We had a sampling duct in the wheel well, so we could measure how much dust gets resuspended as we drove along the roads. And the point here is that the spatial surfaces for the resuspended PM2.5, which is non-exhaust, is very different from the ultrafine particles that come from exhaust. So yes, we can separate those two, but there's more that needs to be separated. Here are some results from our fixed sites, our 40 sites across the city, averaged over 3 seasons. We used copper here as a marker for the brakes, and it's highly concentrated around the roadways. You can see our major highway network here in Toronto, quite different than the nitrogen oxides, which disperse further from the roadways, which is the contrast. So yes, we can see differences between these two. Can they support future health studies? Well, here we looked at the idea of how different was the composition at these fixed sites or from the highly instrumented sites, and we compared them to our Toronto subway, because our Toronto subway is an enclosed space where break-in makes the main contribution. So most of the particulate matter comes from break-in in this system. And there are similarities in terms of the copper concentrations, the iron concentrations, but it's not a perfect mix. So the brakes they're using in the subway are somewhat different than the brakes on the cars. The road dust had a similar concentration to the ambient air, which is not surprising since materials like the copper and the barium in the road dust is probably coming from the soil as well, and so it's the same sort of source for both of them. There we go. We did look at the oxidative potential. I'll only show one result for this. So we saw quite the difference between the particulate matter 2.5 and particulate matter 10 in size. So this is results from about 1,000 filters. So it's a very, very large database of oxidative potential measurements. The other thing that we compared it to is the ambient samples that we had from impact, and we compared it to the Toronto and the Montreal subway system. This is for the glutathione assay. We also did the ascorbic acid assay, the DTT assay. So we did multiple analyses. The Montreal subway, why we're interested in that, it's interesting because Montreal subway has concrete with rubber wheels, whereas the Toronto subway has the conventional brakes, it has rails and steel wheels as well. And we saw a much higher oxidative potential in the Montreal subway. I'm not suggesting this was due to the tires. It's the concentrations of copper for some reason in the Montreal subway are very elevated, and we don't know where that's coming from. So some takeaway messages. I'm almost out of time here, so I'm just going to go for the way forward. we need to come up with easily or deployable methods. So it's fine for us to take high, expensive instruments or to do campaigns where we're out in the field every day, switching filters, switching batteries. That's not going to work for other locations. So we've shown it's possible. We need to find methods that we could deploy to other cities. We need to better constrain the contribution of tire particles. We know from these studies it seems very low. We want to come up with better methods for using high time resolution instruments. So we're looking at using aerosol mass spectrometry to look at these tire particles and the plastics. And we believe there's a lot of potential in the wheel well sampling as well. It's easy to collect the data. It's just very time consuming to interpret it all. So with that, thank you for your attention. I'll pass it on to John. Okay.
Okay. Great, thank you. Hi, everyone. I'm John Volckens from Colorado State University. I'm a member of the HEI Review Committee, and I'm going to quickly provide some thoughts from the Review Committee's perspective on these two studies. Like Greg, I'll have a couple disclosures here. The first one I just told you all, and I'm also a founder of a company called Access Sensor Technologies. So we're focusing on two studies that had quite a bit of geographic diversity. One thing I will remark, though, is that all of these studies are urban studies. And so we need to remember that for the emissions that we see here and the results, they apply primarily to urban form exposures. And that's not true across the world. So the good news is that there's always more work to be done. I'll start with some overview of preliminary results, and this is a table that we've put together between the two studies. The ones that I've highlighted in bold here are mostly on the emissions, and I think this is where the studies did a good job. You can see that when we look at brake wear components between the two studies, you see agreement in the tracer compounds. You also see the same for tire and road wear compounds. And importantly, both studies used different methods and different approaches to characterize the contribution of non-exhaust emissions to ambient PM2.5, and they largely came up with the same findings. This is really important, right? This sort of consilience that we see among different studies in different regions coming up with essentially the same conclusions is really important, and so something the review committee was really impressed with and glad to see. On the health effects side, we certainly see suggestive effects of health effects. This is just one study. It's an acute study. It's done in asthmatics, but an important one, and clearly there was a signal to be seen. There were potentially confounding exposures, of course. When you study non-exhaust emissions that only comprise 2 to 8% of total PM2.5, you have a lot in the soup there that can potentially confound the exposures you see. So some strengths and limitations of these two studies. The first thing, you saw in the last few minutes the smallest window of the amount of work that these two groups did to put these studies together. There is really a tremendous amount of work that has gone into this, and when the reports come out, you'll see that. They're very high-quality study designs, very robust. They use different methods. In some cases, within the same study, they tried to answer one question with multiple methods, and usually those methods came up with the same answer, so very rigorous as well. They're also novel in the fact that they're using both traditional approaches to doing source apportionment and now time-resolved approaches. And again, those approaches tended to agree with each other as well. So a good degree of rigor across the two studies. They focused on real-world emissions, which I think is really important at this stage, right? Chamber studies, animal studies, they all form a continuum of scientific consilience when we try to establish causality, but to use a bad pun, the rubber does hit the road in the real world, and both of these studies were real-world studies, and I think that's a clear strength. I talked about the novel methods. They looked at both population and individual exposures, which is also excellent. I've mentioned a couple limitations. One, of course, is it's very difficult when you're only dealing with up to 10% of the PM2.5 is from this source, trying to look at that source's leverage when there are other sources existing in that mix. That's a real challenge. And as I said before, these were urban studies, and so we probably want to see how these conclusions vary in other geographic regions or in rural regions where, of course, roads can be different and emissions can be different. I'll conclude with some areas for future research. I think we're doing a good job characterizing non-exhaust emissions. I don't think we're done, but certainly a lot of excellent work has been done. I think the next step is really, and I've underlined, to focus on health effects. I think that's probably the next difficult area, the challenge ahead. We want to keep exploring population-level impacts, and that's because the world is changing. The fleet mixes that we see on the roads today, or when these studies were done, may not be the same mixes that we see in 10 years from now. And then I think it's probably about time where we have enough published literature on the topic to synthesize what we know about the health effects. And so for anyone out there who's really hungry to write that next synthesis review, I invite you to begin that, and you can list me as a reviewer. With that, I'll conclude. Thanks.
Great, thank you, John. Next, we'll have Sungju Yoon from the California Air Resources Board.
Good afternoon, everyone. My name is Sungju Jiwoo Yoon. Either go by Sungju or Jiwoo, whatever the pronunciation will be easier for you. So my presentation is about non-exhaust emissions research we have done for the last 10 years as a governmental agency. But still, we need more research need to improve air quality in California. Okay. So some of you may not know who the California Air Resources Board is. ALB, California Air Resources Board, or CAB. It is a unit of California state government. And we are one of 6 agencies under California Environmental Protection Agency. We are the lead agency to fighting for the other air pollution and climate change, try to protect the public health. We do have 2 headquarters in Sacramento and Riverside. Riverside is the world state-of-the-art and state-of-the-science laboratory testing facility for the mobile source emissions. So California has air quality challenges, regional air quality, and also local air quality. In the United States, there are 2 areas having the worst air quality. Unfortunately, both of them are in California. The chart on your right, on your left, shows that the red areas are highlighted. Top one is the San Joaquin Valley, and bottom one is the South Coast Airways. And both areas are ozone extreme non-attainment areas. That is the regional air quality challenge we have. Second challenge we have is emission disparities between communities. It is a local air quality challenges. The brighter the color, the red, orange color tend to have a higher emission exposures compared to yellow and green colors. Most populated areas tend to have higher emission exposure compared to the other areas. The chart on your left showing the current emissions from the other very different sources and our projection for the future 2037. If we implement all the other programs we adopted already, and I'm not going to go over more details, but what I wanted to make a point here is that the mobile sources, cars and trucks and off-road equipment, they are the biggest source of emissions. If we wanted to control regional and air quality, meet the regional and local air quality goals, we have to reduce majority of emissions from the other mobile sources. Recently, we initiated drive forward programs, one for the light duty vehicles, another one for the other heavy duty fleet. And over the last several decades, we have regulated tailpipe emissions much stricter than any other countries and much stricter than federal government. For the first time, we are proposing to regulate non-exhaust emissions in California. So, we have done 2 workshops in October and December last year, and we are still seeking public input. What will be the best strategies to regulate the other non-exhaust emissions, or isn't there any alternative measures to control the non-exhaust emissions? So now our policy is set to control non-exhaust emissions, but still we need to have a lot of research to support the other public policy. So first, I have 4 main areas we have to focus on, and 4 main objectives to do further emissions research for the non-exhaust emissions, to update emissions inventories, and understanding the air quality impact of the other non-exhaust emissions, and characterizing health effect and community exposure. And also, last but not least, California adopted a clean transportation policy more than 10 years ago. And what will be the impact of this clean transportation program on brake wear, tire wear, and wheel wear emissions from rail? We need to characterize the non-exhaust emissions, PM and gaseous emission factors, grams per mile of a vehicle driving. No matter where you want to go and drive, and you are going to drive your vehicle, and your vehicle will emit the other tailpipe emissions, brake wear emissions, and tire wear emissions. The chart shows on your right is the emission and VMT, vehicle miles traveled, projection all the way to 2050. And the orange line on the top, it projects that VMT will continue to grow in California. Green line is for the other tailpipe exhaust emissions. And since we have adopted so many exhaust emission control measures, we are projecting that exhaust PM emissions will be much, much lower than today. Yellow line is for the brake wear emissions. Black line is for the tire wear emissions. One thing I wanted to make a point is that as of today, brake wear PM alone will be on par with exhaust PM emissions. I'm not including secondary PM emissions formulated in the air. It only includes primary PM emissions. So we need to, since we are going to continue to implement the clean transportation program, we have to continue to assess the significance of impact of non-exhaust emissions in the air. Second, air quality impact. We have to characterize the chemical speciation profiles and to understand how they are going to contribute in regional and local air quality, and how much they are going to be involved with secondary PM formation in the air. The brake wear PM speciation profile shows that it contains a lot of heavy metals, and half of them TBD, meaning that we were unable to identify this species because that we haven't intended to identify all. So we believe that this unidentified, the other component will be elemental carbons and electric carbons. Because in California and the United States, we are all using the same brake pad, non-asbestos organic brake pad. So material itself has more than 50% of organic materials. Chart in the middle shows the gaseous tire wear emissions. We just completed our gaseous tire wear emissions measurement study. It shows that all the gases we measured are volatile organic compound, which will be associated with PM2.5 formation in the air. We will continue to assess with these chemical speciation profiles and emission factors, characterized, and what will be the impact of non-exhaust emissions on regional air quality. Now, health effect and community exposure. This is the chart on, we have to assess the significance of exposure to non-existent emissions near source communities. So chart that shows that the oxidative potential of PM particles collected all over the other different locations in Southern California. And the UCLA research team, they have done this work for us. And x-axis shows the other socioeconomic scores, quintile 1 to quintile 4. The higher the score has the other greater potential to expose to the higher emissions. So quintile 4 is, we call the other disadvantaged communities, and they tend to have the greater oxidative potential, potentially has the greater adverse impact on health. The last one is that characterizing non-exhaust emissions and PM and gas emissions, and what will be the impact of clean transportation technologies. And this chart is showing that breakaway PM emissions factor, PM 2.5 milligram per mile, and by vehicle weight. The heavier the weight is, breakaway emissions will increase. And however, electric vehicles, they do come with regenerative braking technologies. We tested the 2 electric vehicles, the boxed in red, and Prius and Model 3, Tesla Model 3. Their breakaway emissions, compared to the similar size and similar weight of gasoline vehicles, was 50 and 75% lower. So there is a huge potential to reduce breakaway emissions transitioning to clean transportation. Of course, we have to continue to promote the new technology development, lighter materials, maximize the friction energy recuperation, and others. And we're still doing a lot of research going on, measuring breakaway tire wear emissions on the road, and zero emissions vehicle breakaway emissions testing, and off-road breakaway emissions testing, and wheel wear and rail wear emissions testing projects. And also, we are having a large health study in the San Joaquin Valley of the California. Also, we are working with the other South Coast Air Quality Management District. They are doing another exposure and health study in Southern California. With that, I want to just kind of emphasize again that thanks to the other stringent tailpipe emission standard, we have reduced tailpipe emissions substantially. Now we are projecting that non-exhaust emissions will be dominant source of fine particulate emissions. And here are the 4 prioritized the research areas for non-exhaust emissions in California. Thank you.
Thank you very much. And our last speaker is going to be Paolo Massatorta. Just press the green.
The big green? Yeah. Okay, thank you. Thank you very much, and good afternoon, everyone. I first would like to thank HAI for inviting us, and Elena in particular to give us the opportunity to talk to you a bit more about the tire industry project. So I will start with the disclaimer. This is not going to be a very technical and scientific presentation. I do have a couple of slides showing like result of some of our latest research, but definitely not at the level that was shown before. And I also take the opportunity to thank all the speakers so far yesterday and today, because I learned a lot. And one of the things that I learned, and it's mainly from the accountability research session of yesterday, it's how important and how linked the air quality to the health is, and especially how much the guidelines and the measure that were put in place in the last 20, 30 years had a positive impact on the public health. But also I learned that there is still a lot to be done, and in particular for some of the source of PM10 and 2.5 that are only little understood so far, and in particular the non-tailpipe emission. tailpipe emissions. So, and that's why we are here, because the tire industry project is indeed try to understand and address any global issue linked to the sustainability of the tire industry. This is an initiative that was initiated by the CEO of 10, if not the most, among the most brand and tire manufacturer in the world. And actually, so that you know, our member cover more than 2/3 of all the tires produced. And also, we are working in close collaboration also with the tire association, the biggest tire association. The project itself is hosted by the World Business Council for Sustainable Development. It took me 6 months to spell it correctly. And it's an NGO based in Geneva, and it's basically there as a third party to ensure the independency of our activities. TIP is structured around the 3 pillars that you see there. The first one being research, the second action and engagement, and the third one communication. And they all work together to try to execute the mission and ambition of TIP with some specific characteristic. Research is really try to understand and clarify the impact of tire wear emission in general. Action has the mission to translate this knowledge into concrete activity and measure that can have can reduce indeed the impact of tire wear emission. And communication, the communication pillar, and our colleagues has the tough work to try to align the voice of all our members around a single message when it comes to sustainability. And I can tell you, it's not an easy work. Actually, I mean, we work with those 10 huge companies, and hopefully there's no one of them here. I can see, because they're very nice to work with, but give us a hard time. And it's definitely to align them around a research program and activity. And if I zoom a bit more into the research pillar that I'm representing here today, we have 3 working groups: emission, transport and fate, and impact. And we are structured in a way basically to do what could be seen as a risk assessment for tire wear emission. If you want, the first working group is trying to understand what is emitted. So we know that tire lose some material. That's why we change tires every now and then. This is not just because the tire manufacturer wants to sell more tire, but it's needed for the security and the safety of this product. So the goal of the emission working group is really to understand and characterize all this material. The second one is to understand where it goes, how much, and how it transforms. Unfortunately, TRWPs are not like the Las Vegas things that whatever happens in Las Vegas stays in Las Vegas. TRWPs are generated on the road, but do not stay on the road. They can travel a lot, end up not only in the air, but also in the river, potentially in the ocean. And actually some research showed that even like in some remote lake of the Alps, Switzerland, for example, where I'm coming from, you could find like some TRWPs. And the last one is really, once we know what it's emitted, where it goes, to understand what are like the potential target, organism target, and try to understand what is the impact. So it's also important to stress the fact that once we align on a 2-year, we work over a 2-year cycle, once we align with the members and have like the roadmap validated by the CEO. We commission this research outside to academia and consultant, potentially someone in this room. And the role of TIP is to manage the project, but also to ensure the quality, the scientific rigor, but also the independency of the research. And all our results are peer-reviewed and published in peer-reviewed journal. Again, and I don't know, this is 11 minutes is my time?
We're a little tight on time, but keep going.
Okay, sorry. 4 minutes, thank you. So we are not old as HEI, but we do have like 20 years on our back. I mean, not me, I joined this organization only 20 months ago, but 20 years ago, this was relatively new. Again, we know that we had to change the tire, but we didn't know exactly what was this material that we were losing. So at the very beginning, a lot was our research was around understanding what are the TRWPs, what are like the characterization of them. For example, we know that half is from the tire, but half is from the road itself. And then, of course, the more you know, the more question you have, as always happens in research. So from them, we evolve in the last few years, and actually this goes in parallel to also the scientific interest that grow around TRWPs. Now there are a lot of new university and scientists and brilliant scientists that are working on it, and we also start trying to build the toolbox and the tools for the science to grow. For example, making sure that to develop the right standard. So, for example, ISO or ACD standard, we are very much involved in pushing this forward, but also to define and specify reference material for other scientists to study the effects. So lately, again, and you see here the TIP 2.0 that happens a couple of years ago when really our member felt the need to really expand our scope and mission, and we are really going more towards like understanding the impact of tire wear emission. Here is just to show you the complexity of the things that we are dealing with. Of course, here you're a super expert and you know, and that's why I'm here actually to learn from you the volatile part and what goes in the air, so the airborne fraction of our emission, but you're also dealing with the particles themselves, the particles that are a bit heavier and just stay, as I mentioned before, either on the field or next to the road or enters like the stream, the water streams, and could potentially end up in the ocean, but also the leachable. So the leachable are all these chemicals that are used by the tire industry and transformed during the process and the manufacturing, but also transformed during the life, because the tire undergoes a lot of stress and a lot of chemical transformation are happening. So all of these, it's in scope of our research. One other little slide that I want to share with you, again, this is probably like, I hope it's the most relevant for this group. It's a recent study that is currently under review and is hopefully going to be published soon, but I can only show you what is in this slide. It's a collaboration we are having with the University of Cambridge, where we are trying to, where we have developed an approach to study nanoparticles as they are produced. So this is a lab. This is again goes in the direction of the characterization of the emission of tires, and to build standards and to build methods that help potentially other scientists to continue on the research. The second example of our research that I want to share with you, it's something that has been published beginning of this year, and it's something that at least for the tire industry was a huge challenge. This little chemical called 6-PPD. Again, I know it's not exactly what is in scope of the HAI, but for us it's super important because we look more and more as the particle as a vehicle of potential toxic chemical, and this is a classic example. This chemical is suspected to be harmful for a specific kind of salmon, the coho salmon, that is actually living in northwest of North America, and it's suspected to kill a lot of these fishes. So this is currently being regulated in Europe, for example, and just to show you again an example of how TIP is working, we were involved very much in providing data to the European Commission so that they could come up with the right regulation and so on. So this is simply our study that show how much this specific chemical, the half-life of this specific chemical in different conditions, and his potential to bioaccumulate in the food chain. Just to summarize again, the intention here was really just to simply show you who we are and how we operate, and potentially seek for collaboration and contribute for the discussion that we have. Because again, as much as we know about TRWPs and some chemical, the volatile will still, at least for our industry, something that is perceived as a big gap where a lot has to be improved. And then I will just leave with this last slide on, which is a bit of an advertisement on a conference that is organized every year. And actually last year we had the pleasure to have some of you contributing to this event that was in Boston. And again, thank you for your contribution. And this year is going to be in Cambridge, UK, beginning of December. So you're all welcome to join. And sorry for being a bit longer.
Okay, great. We're going to jump right to audience questions in the interest of time. So please come on up to the microphone.
And please introduce yourself before you ask your question. Thank you.
Thank you very much. Yifang Zhu from UCLA. I'm just curious about the two studies that presented today. Do you have a rough sense about the percentage of electric vehicles at your study size relative to the whole fleet, ballpark? I think that, just put the context about the less than 7%, 8% total PM 2.5 attributable to brake and tires. What is the EV, like non-exhaust component in the fleet?
I'd say in Toronto, Vancouver, we're about 2 or 3% actually in the fleet electric vehicles, not some mid-sized trucks that are electric, no large ones.
I'd say about 5% in London, the big low emission zone, and that's driven the fleet change in London. A lot of the taxis, I think the taxis are almost exclusively electric now, so it would be higher in.
Hi, Chris Carlson, University of British Columbia. Thanks to the HEI for supporting this work. Paolo, it's a bit of a detail, but hopefully not too much in the weeds. On your diagram of the exposure pathways, I looked at it several times to make sure I hope I don't misspeak, but you had humans at the bottom, and then you had plants and whatnot, and at the top you had leachate, and there's no way on your diagram for leachate to get to humans, which I found odd, because I think we were talking yesterday, leachate is probably actually quite important, so I'm curious about that.
No, is it open? Yeah, you're totally right. Actually, I'm showing what the expert or that scientist has published, but actually we have a new version of this that not yet published and will be, where you see like the human as the end receptor of many. I mean, there are studies that have showed that some of these tire-related chemicals can enter the food chain in leafy vegetable. They're uptake in some leafy vegetable, and indeed one of the new venues that we are studying is indeed to see what is the potential risk for humans. Yeah, but you're totally right, yes.
Thanks for the very informative discussion. I'm Jia Chen from the University of Southern California. I was curious about the mitigation strategies for non-tailpipe emissions. Like for brake-wear, you have regenerative braking. For tire wear, what are some of the solutions that tire manufacturers and regulators are thinking in terms of reducing their emissions? And also potentially the toxicity, like are there trade-offs between the mass versus the toxicity or things like that? I'm just curious in general. Thank you.
That's a great question, and we are asking that question to ourselves as well. But as you know, there are established test procedure to characterize breakaway PM emissions. I'm talking about airborne particles. However, there is no such a standardized test procedure for tire wear emissions at this point. Many research groups, and including us, we are developing new, like a repeatable, reproducible tire wear measurement method, but still there is no such a method is there. But we know the other tires is organic compound. It not only creating fine particulate matter, but also it potentially releases a volatile organic compound. It will give a huge impact, or I don't know how much, but it will give an impact locally and regional air quality. So what will be the other health impact of all those? Those are all the subject, and we need to further investigate.
Hi, thank you so much for the presentation. Unfortunately, I only was able to listen to Paula. Can you please, I was wondering whether the tire project has considered tying tire-related emissions into mobile source emissions, particularly in urban environments where there is significant truck traffic related to warehouse traffic, particularly in Chicago, for example, in our EJ communities where we have a large number of warehouses. Truck-related diesel PM emissions are a significant concern in terms of air quality and also health effects. Do you have plans to tie the emission estimates that you're obtaining from your study to inform us better on mobile source emissions from trucks, particularly in urban environments?
That's a great question. So when we are characterizing emission factors, for instance, like tailpipe emission factors, we do factor in vehicle operation, how fast the vehicle is driving, what are the other acceleration and deceleration profiles. But we don't have any of those when it comes to characterizing tire wear emissions. Yes, and depending on the other location, depending on vehicle operation, depending on the pavement type and environmental factors, tire emissions are going to be very much different. But at this point, we don't know. I presented you a tire emissions projection all the way to 2050. That is one single number. It doesn't vary by vehicle operation characteristics. So it should be updated. So that is one of the first priorities we have to characterize with the right method reflecting real-world driving conditions and characterize emission factors so that we can update the emissions inventory and we will know what are the magnitude of emissions coming out from tires. Then we can come up with air quality plans, how we are going to mitigate these emissions. So just kind of, if I say long, and I'm not saying like 10, 20 years, but still a long way to go.
Thank you. This is, by the way, Sarah Erdahl at University of Illinois, Chicago. So thank you.
Let's go over here.
Thank you. Thank you for all your interesting talks. And I think that my question was somewhat approached by that last answer, but it seems to me that that when we go out and measure brake and tire wear particles, we get numbers that we get contributions to the total PM load that are considerably lower than what the emissions inventories suggest, but like kind of by a lot. So I was wondering if you as a panel could share your thoughts on that apparent discrepancy.
Certainly, I'm a big advocate for real-world field measurements. And so, yes, I think it's important for us to track the changes, and this will be increasingly important as we implement changes such as the Euro 7 standard or the ambitious goals that California has to see if we are actually reducing it. So having methods to measure is quite important. I won't comment on the model values, the MOVES values, because I didn't.
Sorry, did I forget to say who I am? I'm Suzanne Paulson from UCLA. But yes, I'd like to hear about the...
Yeah, so I'm not in the emissions inventory development team. However, the way we develop the emissions inventory is the same methodology we used, like US EPA used to update their MOVES model. It was based on the literature review, and which, I mean, let's say step back. 1970s, there was an AP42 emissions factor for tire wear emissions. That emissions factor was kind of corrected and adjusted and modified based on the literature findings. Now, there are so many literature studies out there and measurement done in the field. Are those methodologies comparable? Can we translate one number to another? It was almost impossible to do that. So when we are saying, I talked to emissions factor we are using for the emissions inventory is only one number. But that number are going to be varied by depending on the number of tires. But then this the one number, depending on who will measure, emissions are going to be order of magnitude different. When it comes to emissions inventory perspective, we have to come up with some consensus number, which will be median or average value. So I'm not saying that the tire emissions inventory is wrong, but there is a certain magnitude of uncertainties are involved with.
Hi, this is Anarelli Morales from Weld County in Colorado in the Public Health Department. My question is about, I guess, jurisdictions and authority for reduction or regulatory measures for NEE. Since it's not coming from the tailpipe, would a state not being California be able to put regulations up that are reducing non-exhaust emissions?
Well, regarding the other criteria of pollutant, such as nitrogen oxide emissions and PM2.5, came from tailpipe. That is under the federal jurisdiction, and state government get a waiver and develop their own regulations. But when it comes to air toxics, state government has a jurisdiction.
Okay.
So PM2.5 is air toxics. PM2.5 from the brake wear, it contains a lot of heavy metals. Gaseous emissions from tires contains a lot of VOCs and PAHs. So in a air toxics perspective, we do have a certain level of jurisdiction to control. Okay. But not sure how comprehensively we can control to meet the federal air quality standard.
Thank you.
Chad Bailey from US EPA. I guess, I think Suzanne Paulson had a good question about inventory versus ambient, and I guess my question is for those who've done the field measurements, both the UK and Toronto teams. I know you guys met, I think, Greg, you said you kind of threw everything that you could at it to sort of figure out how to characterize it, but is there a simple answer to that? I know there have been you know, the Meredith Franklin study, they were using like I think it was either ICP-MS or XRF on, you know, on some old filters and using these metal tracers. But like, from your perspective, like, do we yet know what to measure, you know, short of throwing everything at it?
Yeah, thank you for the question. I do believe we know what to measure. So metal tracers that we can use, I think we've shown that that works. The complexity, the challenge is that whether it's our study, Meredith's study, to put out field samples and collect samples is a whole lot of work by people. And so to try to encourage organizations, governments to do this on a routine basis is going to be difficult. And particularly given that non-exhaust emissions are very heterogeneous across the city, it's not going to be a case of putting up one sampling site and collecting filters. We're going to have to collect filters in many, many locations, which is going to be a lot of people, a lot of person power. So that's where I see the problem. I don't see the problem as once we get the samples, knowing how to analyze them in the lab. That I think we have shown that it's feasible.
Hi, Mike Jarrett, UCLA. I have a comment and a question. I first want to thank all the speakers. That was an outstanding session, so thank you for that. The comment is, you know, I think if we're going to have an integrated approach to dealing with brake and tire wear, we should not forget that the best way to reduce it is to drive less. And that involves compact development that's transit-oriented, walkable neighborhoods, destinations that people can walk to for their everyday needs. And I applaud everybody for the rigor that they're putting into quantifying the particles. We're trying to do similar things at UCLA. But I think we have to keep that bigger lever in mind and, you know, consider doing simulations to say, well, what would happen if we had fewer cars because of these interventions? How much would that reduce the emissions? And then the second thing I wanted to ask about, which I've been thinking about, but I don't know a lot about the measurement of it, is what do we know about microplastics that are coming off the tires? And if, you know, have there been any studies where these are quantified? What are the measurement options that are available?
So thank you for the question, Mike. And I agree completely with your comment, and we should have highlighted that in the talk, that if we don't have wheels on the roads and people pressing the brakes, the emissions will reduce. So yes, walking is the better way to go. In terms of tires, in terms of microplastics, we've only looked at the rubber composition. That is the main component in tires, and the analysis for that, for the natural and synthetic rubber, that is pretty straightforward. The health impacts associated with it, that is open. It's such a complex mixture with so many additives in it. And I think I'll come back to the point that was made earlier about the health impact. Reducing emissions through things like the EU 7 standards is a good way forward, but we shouldn't fall into the trap of believing that reduced emissions will necessarily equal better health. It really depends what's going to be in these emissions, and I think that's an important consideration, particularly if there is reformulation of things like brake pads and the rubber. We want to make sure we don't go the wrong direction unintentionally. So that is a reason, I think, for continuing to work in this area.
Greg, let me just build on your comment there. So the assumption is that if people drive less, you know, they might take more buses, and then we also have lots of trucks on the road, which, you know, people driving less doesn't necessarily eliminate. So what's your sense of like how much of that contribution, you know, is amenable to reduction in passenger vehicle traffic, which was Mike's point, versus, you know, if the biggest percentage of that is coming from heavy duty vehicles, then reducing passenger traffic has other benefits, but not necessarily that.
That is a fair point. So certainly for the exhaust emissions, it's the freight, and it's not just the freight, it's a very small portion of the trucks that are the heavy emitters. And so we've looked at that in other studies, and it's a very small portion of the fleet that makes most of the contribution. So if I'm being a good citizen and walking along the road, there's still just as many trucks, we don't expect to see that drop down. For the road dust, it is more coming from the cars, and so that would drop down. For the brakes, it's in between. I think the way forward is more of the studies show that regenerative braking reduces the emissions, and hence, as we move towards hybrid and electric vehicles, I think we will see the reductions in the brake emissions. But fewer vehicles would be a better way forward.
Okay. And does the regenerative braking of electric vehicles, how does that change sort of brake wear and emissions?
In order to stop a vehicle, you've got to put the kinetic energy somewhere. Mm-hmm. So it's either going to go into heat by heating up the wheels, the brake pads, or it's going to go in braking bonds, which is the physical abrasion. Mm-hmm. That energy's got to go somewhere. The best place for it to go is into a battery. Mm-hmm. And so it's not surprising that more of the studies are showing that if we use regenerative braking, there's nowhere near as much abrasion, and the amount of emissions go down.
Hi, Chair Bailey from US EPA again, and this is a question for Paolo. I guess I'm going to ask you kind of a naive, well, excessively naive question. Why don't you just design tires to emit no microplastics and have no 6-ppd? Like, why don't you just make products that are good for the environment? Like, in other words, like what? Like when you're designing a tire, what are your considerations? What is industry thinking about when they make a tire?
Thank you for the question. I'll go straight to the CEO the next time I see them. No, I'm sure they have an answer. No, actually, I mean, TAP, I was discussing before on the table with the colleagues here, operates in a non-competitive space. So this is definitely going to be a competitive space for our members. So it's something that we don't explore. Now, and just to comment on your comment, it's true that less tire and are going to be less emission, but also the number one driver or the number one element for the tire emission is the drive style. So it's not only how much we drive, but also how we drive. Cornering, braking, and all of these has a huge impact on the abrasion. So it's also down to all of us to be a bit more responsible, not only on how many kilometers we drive, but also on how we drive it, and this has been demonstrated. And I think the Euro 7 regulation is going in that direction. I mean, abrasion rate is going to be lower, that's for sure. That's where everybody wants to go. But as I was mentioning before, some part of abrasion need to be there. I mean, there won't be any any safety tire without any abrasion. So, of course, technology can improve, and I'm sure the member of TIP are going in the direction in the compounding, in the design, and all of these. But we have to, accept that abrasion is part of the tire. So we'll never get out.
Just to sort of build on that, when I talk to engineers, they ask, how, from a health perspective, how should the tire abrade? They can make something that produces a very small particulate. They can make it under different environmental conditions and under different driving conditions. But we need to give the industry a steer into what they need to create. They can design the tires to meet certain requirements, but at the moment we don't know under which conditions the tire pollutant is most toxic, or if it even is toxic at all.
but that's exactly what we are trying to do, to understand. I was stressing a lot to understand that part. We as TAP are not going to design the new tire, but what we are trying to do is really to understand exactly the characteristic of what makes maybe this particle less toxic or something like this, or to build, as I mentioned before, how you measure the toxicity of these TRWPs, because still a lot to have to be understood, but that's how we as TAP try to contribute. And the open door that we have with the tire manufacturer, I think it's an advantage that we have, and being able to sit at the also scientific tables like this, I think it's a good, it's the perfect example of how we should try to improve things. Because if we convince the CEO, that's when the change is going to happen.
So we're at time, and before I conclude, I want to do two things. One, I'd like to acknowledge the HEI staff that contributed to this exciting session. That's Allison Patton and Eva Tanner, who did most of the work to make this happen today and make this cutting-edge research so informative and exciting. I'd also like to thank all our speakers today who were invited to talk and for the great research. So please join me in thanking everyone.